So yesterday, quick recap, we stayed with the topic of factoring. Specifically, we introduced the asterisk method, which was particularly useful for factoring quadratic trinomials. So it's three terms, highest exponent of 2. Hopefully with the assignment yesterday, that practice with the asterisk method made it seem a little less strange, I hope. Particularly because we're going to reuse it again today. Because so far during this unit, we've talked about exponent properties. We've done all the operations with the polynomials, adding, subtracting, multiplying, dividing. We spent a couple days on factoring, whether it was greatest common factors, grouping them if it had 4 or more terms, or yesterday we did the asterisk method, but so far they've all just been expressions. Now, typically, once we learn how to manipulate new types of expressions, we then, once we feel comfortable, hopefully, we bring in the equations. So this was all meant to build up to a point where we could then solve these new equations that we haven't really encountered before. And we're going to use some of the skills we've picked up the past few days. Before we do that, though, there is a property that we're going to use along with our new skills that's going to allow us to kind of get over a hurdle and find our solutions today. And that property is the zero product property. Now, if you don't remember it by name, that's okay. Odds are you probably already understand what it does, just maybe not specifically in terms of mathematical statements. But the property says that if a product, so the result of a multiplication, equals 0, then at least one of the numbers being multiplied must also be 0. So again, shouldn't shock us because anytime we multiplied by 0 in the past, we know that we always got 0. And it doesn't matter how many things you're multiplying together. If you had 100 different numbers multiplied together, but only one of them was 0, immediately, as soon as you see it, you know that the result's going to be 0 because no matter what you multiply after that, it's always going to stay 0. So just a very brief statement here, just to kind of tie it into what it looks like in an equation. It says here that if you have A times B times C times D, and you know that that product equals 0, then at least one of 4 things has to be true. Either A would have to be 0, or B would have to be 0, or C would have to be 0, or D would have to be 0. And in fact, it doesn't actually matter which one is 0. In fact, 2 of them, or 3 of them, or all of them could be 0. But what has to be true is at least one of them is 0. Now, that property is going to come back again here in just a moment in our steps for solving quadratic equations, but hopefully that doesn't shock you. That's something that we've been multiplying with zeros for some time. It's usually the thing that we prefer to multiply with because it was always the easiest case. But it's going to have stronger implications as we bring it into some slightly more involved equations. So here we have some steps, and these steps I'm going to add a couple little side notes here, I think, at least one. These are going to be the steps that we follow one at a time in order to solve these new types of equations. Now, you can't skip steps, and I would strongly suggest don't try to do them out of order, because otherwise, when you get to the factoring section, what you're factoring may not actually be what you should be factoring. And I'll show you here. I think on the back side we have some examples that fall into that category. So the first thing we're going to want to do, well, first off, make sure it is a quadratic equation. An equation, of course, will have the equal sign. Quadratic, we've talked about for a couple days now, means that the highest exponent on any of the variables is a 2. And if that all is true, then what you're going to do is follow these steps. First off, move all the terms to one side accordingly to set the equation equal to 0. set the equation equal to 0. The zero product property will be of no use to us if your equation is not equal to 0. So sometimes that'll be done for us. Sometimes we're going to have to move some terms from one side to the other, but those are things that we've done before in previous units. Once it's set equal to 0, second thing you want to do is factor it. And to do that, or the reason why we want to do this is because we want to take whatever the polynomial is and we want to break it down into smaller parts or factors. Now those might be monomials, they might be binomials. Hopefully they're not trinomials, because usually if we still have a trinomial, it can be factored down a little bit further. But there is a reminder there, which is worth highlighting. Don't forget to check for that greatest common factor first. That was actually a comment we threw in our notes yesterday, because the asterisk method, although very handy, does cause that greatest common factor to disappear a lot of the times. It really does help us to set it aside early on. Third thing we want to do is, once we've had it set equal to 0, we factored it as far as we possibly can. We want to then set each factor, again, monomial, binomial, and so on, equal to 0 individually. Now, I kind of blanked for just a moment. Up here on step 2, I should have written that factoring could be greatest common factors. It could be that you're using the asterisk method. Or it could be that you're using that special case we introduced yesterday as well, which was that difference of perfect squares. So again, in the factor phase, it doesn't tell you how you have to factor. And in fact, I probably should have also put factor by grouping in there as well. But anytime you hear factor, all those options are on the table, so long as you check for the greatest common factor first. It's step 3. This is actually where the zero product property is being utilized. Because the zero product property says that if you have a product set equal to 0, at least one of the parts of that product must itself be 0. And we'll see this in action here momentarily. Last but not least, once we've reached this phase, we're going to end up with at least 2 smaller, I'll even say simpler equations that we can then solve for to get all the solutions for that original quadratic equation. So typically we'll get at least 2 solutions. Sometimes we might get exactly 1, but it's that last step, solving these little mini equations, I like to call them, is going to give us our final solutions. So again, these steps may mean nothing yet because we haven't actually tried them, but this is something that once you see the practice, once we've done a few together, while you're doing the assignment later, it may be useful to have these steps nearby so that if even when the equation changes, you can go back and say, okay, what do I do first? Once I've accomplished that, what do I do next? And so on and so forth. So we're going to jump right into it. Some practice problems. I'm going to cut everything else out there, give you guys a quick second to jot that down. Grab me a copy of the notes as well so I can read the steps exactly as they're written in our notes today. And let's see here. For the sake of consistency, I'll put a little guideline there. I'm not going to go too crazy because actually I'm going to go even shorter because my steps here are going to be fairly brief, but you'll see what I mean here once we get to that phase. So first off, I know it's a quadratic equation because it's an equation with the equal sign. It's quadratic because the highest exponent on the variable is a 2. So I know that I need to use those steps. Step 1 is to move all the terms to one side accordingly to set the equation equal to 0. Is there anything we need to do here to accomplish that task? Add m squared and 10m together. Real quick question. Are those like terms?
No.
Why not?
Because 10m isn't squared by anything.
Right, so this m is not being squared. So this is almost as different as if this was an x and this one was a y. So an m squared is not the same as an m. So unfortunately, there's no like terms, but good thing that we always need to check for them, because if there ever are like terms, usually it's a good idea to combine them earlier. But once we've got this set here, we want to move everything together to set it equal to 0. So I guess let me rephrase it this way. Is this one set equal to 0?
Yes.
Sure. So if at least one of the signs is already set equal to 0, step 1 won't require any attention. So then I'm going to go on to step 2. So step 2, I'm going to factor the quadratic polynomial. In this case, it's specifically a trinomial, to break it down into smaller factors. But the reminder was, don't forget to check for a greatest common factor first. So maybe it would help also put the one that's hiding there in front of the m squared term. Are there any greatest common factors that I can take out of all 3 of these terms other than 1?
2.
So,
Oh, there's no other.
well, 2 would work for the 10 and the 24, but what would it fail at?
1.
The 1, because if you try to divide 1 by anything other than 1, you're going to get a fraction. So 2 would work for 2 of the 3 terms, but remember, greatest common factors have to work for all the terms. So although we needed to check, this time there weren't any that we had to worry about. That's okay. So the next thing I'm going to do is I'm going to think, okay, I'm factoring. This looks, at least this left-hand side looks a lot like the quadratic trinomials we were looking at yesterday. So I say, okay, well, let me think about it in that term. It's already in descending order. We've already considered the greatest common factor. Maybe I can pull out the A, B, and C I would need. So this is going to be kind of like a side step. What's my A?
1.
Close, just the coefficient, which is 1. What's my B?
10.
Is the 10. And my C
24.
is the 24. Good. And Marissa's on the chat here. Make sure credit is given where credit is due. She's following along with all those as well. So these are the values that we used yesterday for that asterisk method that we introduced. Now, I didn't provide asterisks today because not every single equation we solve will necessarily need one. But if you're ever trying to come up with an asterisk, remember, my suggestion is just draw an X and then follow it up with drawing a horizontal line through it. So going back to yesterday's topic, A times C will go on top. So 1 times 24 is 24. A on either side would give us 1s. B on the bottom is going to give me a 10. So hopefully you recall from yesterday, whatever 2 values we choose have to multiply to equal the top, but at the same time have to add to equal the bottom. So 2 numbers that multiply to equal 24, but at the same time add to equal 10. Hopefully you still have your factor pair list, which I realize, Toby, don't let me forget, I'll grab you one of those today as well. But I would look at that list at 24, and I would look at the factor pairs there. We should see 1 and 24, 2 and 12, 3 and 8, 4 and 6. Which of those pairs would also add to equal 10?
Didn't you say 2?
I said 2 and 12, which that seems tempting. 2 and 12?
Yes.
Okay, let's check it.
I'd say 4 and 6.
You're saying 4 and 6, so we'll hold that thought, because if this doesn't work, we can try 4 and 6 as well. So I kind of see where you're going with this, Toby. 2 and 12, technically they have a difference of 10. So in order to add to equal a positive 10, I believe you would need the 2 to be negative. Is that correct?
I guess so.
Well, negative 2 plus 12 would be a positive 10. But what's negative 2 times 12?
Negative 24.
Negative 24. So although we could get it to work to add to equal positive 10, it did require us to make one of them negative. And the problem with that is if the signs are different, it's going to multiply and it's not going to equal the positive value that we're looking for. So I put this one on here because sometimes you may have two different pairs that seem like they could work for different reasons. So you weren't wrong. You looked at a really useful pair here, but it just so happened because of the way the signs are going to have to work out, we're going to have to go with the 4 and the 6.
I did a couple yesterday where I had to like go back because I did that where I like made a negative and then changed up the whole problem. So I did the same thing.
Yep, that's absolutely why it's worth a quick mental check before writing out your binomials. Ask yourself what's 4 times 6. Hopefully you get a positive 24. And then ask yourself what's 4 plus 6. It's going to give you the positive 10 that we're looking for. So there are going to be a few that come up that are a little bit tricky. Some of the pairs, you may have two pairs that kind of seem like they could work. You're not going to know what the correct answer is until you play around with them a little bit. You cannot be afraid to make mistakes here because that is where we figure things out. It's where we develop good habits. So with the asterisk method, it gives us these two useful pairings of numbers, which we want to make sure real quick that if they can simplify, that we do that. But I do believe that because of those ones, they really can't get much smaller than that. So we're still going to have 1 with the 4 and 1 with the 6, but we can now bring back that variable that we've kind of been ignoring for a while, which is the letter M. And yesterday, if you recall, we slide that in on the top with whatever values sitting there waiting for us. Now this whole big kind of unusual process, what it's allowed me to do now is to, instead of having that quadratic trinomial, I now know the two binomials that multiply together to make it. And those two binomials are 1m plus 4 and 1m plus 6. And that whole equation is still set equal to 0. That's a key part. So off to the side here, we had to do that. That was for the factoring. In fact, if you need to, maybe even remind yourself that that was a process we used to factor. That was step 2. Step 3, now that we have factored the m squared plus 10m plus 24, step 3 says set each factor, in this case, both binomials, equal to 0 individually. So I'm actually going to put a little side note in here. This is step 3, which is all thanks to that zero product property. And according to the zero product property, if you have a product, in this case, a binomial times a binomial, and that product is equal to 0, the zero product property says that either the m plus 4 would have to equal 0, or the m plus 6 would have to equal 0. So that's why step 3 says set each of those factors equal to 0 individually. So what we end up with here is that we know that either m plus 4 has to equal 0, or the m plus 6 has to equal 0. Now you'll notice the little equations we end up with here aren't difficult ones. In fact, this goes all the way back to day 1, if you can believe it. How would you solve that first mini equation?
Add 4 and
That 4 is already being added to m. How do you solve for a variable?
don't you divide?
How do you solve for any variable ultimately? We try to get the variable by itself. Is this variable by itself?
Yes.
Completely by itself? There's nothing on this side right next to it here, right here? There is a plus 4. So to make that 4 disappear, we do the opposite. We do a minus 4. Whatever we do to one side, though, we always do the exact same to the opposite. So on the left, 4 take away 4 is 0, which is why we can hide it. That leaves me with just m. On the right, 0 take away 4 is a negative 4, which gives us an answer. But we're not done, because there is a second possibility that we must consider. We have to consider what m would have to be in order for m plus 6 to equal 0. So how would I solve that second mini equation? Add a 6? We want to minus the 6, to subtract the 6 from both sides. So the 6 minus 6 on the left is gone. Leave me with m by itself. 0 take away 6 leaves me with a negative 6. So I ended up with 2 results, which I didn't actually specifically say it, but we just did step 4. We solved each of these little equations together. So what I end up with is 2 solutions. Now, depending on your comfort level, sometimes people freak out at this. If you want to just box these in and say, I'm done, I'm great, I'm happy, that's fine. What you will see on the assignment today, and this is the technical way of writing it, is anytime you have more than one solution, usually you write it as a set. Not an ordered pair, a set. So if I was to write this out, I would list negative 4 with negative 6, but I'd wrap it with braces instead of parentheses, because a parentheses would make me think, oh, that's an ordered pair. Where's the point? Negative 4, negative 6. No, we're not talking ordered pairs. We're talking solutions. So once you look at it, it looks a bit busy. We've kind of got some work going on here at the side. That was our factoring. Then all of a sudden we do a little jump to where we kind of split our one equation into 2 smaller equations. But again, the reason for that is the zero product property says that at least one of those had to equal 0. So instead of just leaving it to chance, we figured out every scenario that would cause one of those to equal 0. And what we come up with is that there are 2 answers that would work here. If you were to plug in negative 4 for both of these m's and solve it, simplify it, you'd get a true statement. Same if you plugged in negative 6 to where the m's are. If you simplify that with your order of operations, you get a true statement again. These are the exact 2 answers, the only 2 answers that work for this unique equation. Okay. So let's try another one. I tried to give some variety today without killing you with boredom, because we could do 50 of these and have a unique one every single time. But that's where the practice comes in for you guys later. But let's take a look at this second one. I have my steps here next to me as well. I know it's quadratic because the highest exponent is a 2. And I know it's an equation because I see an equal sign. So I know that these steps are going to apply here. So step one is move all the terms to one side accordingly to set the equation equal to 0. Is this equation equal to 0? Yes. So step one, already done. Step two, factor. So factor the quadratic polynomial to break it down into smaller factors. This is where that reminder was. Don't forget to check for a greatest common factor first. Now, this one's a bit sneaky. What type of polynomial do we have here on the left? Monomial, binomial, trinomial.
Try
So what are the three terms?
35 and 0.
Ah, 0 is not on the same side, so 0 wouldn't be counted. So it's a binomial, okay? So already I'm thinking, we didn't use the asterisk method for binomials yesterday. So this is kind of unique. But I shouldn't even be thinking about the asterisk method yet because I should be asking myself, is there a greatest common factor? Which essentially is just me asking, is there anything these two terms have in common? So Miranda's saying 1. I would agree that the greatest common factor of 3 and -5 is going to be 1, but we can't just think about the coefficients. Is there anything else they have in common? Nothing at all.
Nope.
Nothing even slightly similar.
15.
Well, they would multiply to be 15, so we don't want to go larger because factors are usually smaller than the values we're considering. Miranda has an idea, but she's not terribly confident. She's got a little question mark in there. She's asking, what about x? Do they both have an x?
Yes.
Yeah. How many do they both have?
1.
They both have at least 1. Wouldn't that be something in common? Both have an x. Right? They have an x in common. And my question for you, Toby, then, you said 1. This one has 2. Why can't I take 2 away from both?
Because -5x doesn't have 2 here.
That's right. You can't take more than what the smallest one has, the smallest amount that's available. So yes, 1 for the coefficients, that's not going to be too exciting. But because they both have at least an x, my greatest common factor can also include the x. So just for the sake of our notes here, put a little side note that this is our greatest common factor that we found. I didn't put my little highlighting in there. Not long enough. Shame on me. Now, rewind, today's Wednesday, so rewind back to Monday when we were working with just greatest common factors. What we always did first was we set it aside before we divide. So I found the greatest common factor, set it down here to the side. When I divide it out, what is 3x squared divided by 1x going to give me? Close. What's 3 divided by 1?
0, right?
Think about that. 3 divided by 1.
Yeah.
3 pieces of pizza, 1 person to eat them. That person gets how many pieces of pizza?
3.
All 3. 3 divided by 1 gives me 3, but you were right about the x. There was 2 of them. We only took 1 away, so there will still be an x on that first term. What about -5 divided by 1? It'll be a -5. Will that one still have an x?
Oh,
Nope, because there was 1 there. We took that one away. Pause while I adjust my OCD. So we took that one away. So we should get 1x times the binomial 3x minus 5. Now, if you're worried that you've misplaced something, mental check. 1x times 3x, if I were to distribute, 1x times 3x should give me that 3x squared again. 1x times -5 should give me a -5x. So I haven't lost anything. I've just changed the way it looks by factoring. It's still set equal to 0. And what I'm left with this time, a little different, is a monomial times a binomial. Now, you should always be checking for any other opportunities to factor even further. But because of this one being unique, the monomial 1x, well, that can't get any smaller. And the binomial 3x minus 5, we already took everything out they have in common. We can't use grouping here because that's usually at least 4 terms. We can't use the asterisk method anymore because, well, for 2 reasons. It's no longer quadratic, and it's not a trinomial. So this one, albeit a little bit boring, factored very quickly with just a greatest common factor set aside. So step 2 is done. Not as extravagant as the last one, but it is done, which means then I go to step 3. And step 3, this is again where we say, I have a product set equal to 0. Why not consider the 0 product property? And the 0 product property says that if you have a product, say maybe a monomial times a binomial, and that whole product is set equal to 0, then at least one of the parts of that product itself must be 0. So we come up with 2 conclusions. Either 1x has to equal 0, or 3x minus 5 has to equal 0. We don't care which, because at least one of them has to work. So we're going to consider both. How would you solve the first one? 1x is the one that
You would divide.
you caught yourself, even before I could say anything. So the 1's right beside it, so we would divide both sides by 1. And it was important, but this one's not terribly interesting because 0 divided by anything is still going to give us a 0. Second one's a little bit more not interesting. 2-step equation. What would you do first?
Add 5.
Add 5 to both sides. See, Toby, it's starting to come back to you. You're waking up. That's what you're doing.
A little bit.
So the -5 plus 5 is gone, leaving us with just the 3x. The 0 plus 5 gives me 5. Again, ignore me while I tend to my OCD.
OCD,
Maybe not. I don't know. It seems like it some days, but
ADHD.
not diagnosed. Again, I don't know. I haven't been diagnosed with it. So have we finished solving that one?
No.
What do we still need to do?
You need to divide.
Divide by 3. Now here's where students get a little bit worried, because if you're doing this in a calculator along the way, your calculator is going to give you a decimal at this point. I would say, so long as the fraction is simplified, it should be okay if you leave it as an improper fraction. 5/3 doesn't simplify any further. Now, again, if you're worried, or depending if this was you measuring something out, you could do a mixed number. 3 goes into 5 one time, which is 2 shy of 5. Or your calculator is going to tell you that this is 1.6 repeating. Again, depending on what you're doing with these answers, maybe one format is better than the other. But for right now, there's no story attached to it. It's just solving. So any of those answers would work. I personally, though, I leave mine as an improper fraction. If there's nothing more I'm going to do with it, I just make sure it's simplified and move on about my day. There's my second problem. So we follow the exact same steps, but you'll notice, depending on what the factoring step requires, we may have a lot going on to factor, in which case we use the asterisk method or something like it. Or the factoring may be just a really small, tiny step where all we do is divide out a greatest common factor. Either way, we factored, but not every scenario of factoring is going to look the same. Regardless, those steps still let us through the process. So not too bad to start off. Naturally, though, we got to pick up the difficulty a little bit, because so far these two equations were very kind. They both already started off being set equal to 0. Well, that's not always going to be the case, which is why on the next two problems, you'll notice very quickly that these are not set equal to 0. So step 1, we're going to have to require, or is going to require, a little bit of manipulation before we can move on to step 2. So starting with the first, kind of get my bearings here.
What was two?
This is number 3.
What was two?
I'll go back later. So step 1, move all terms to one side accordingly, set the equation equal to 0. Is this one set equal to 0? No. We have 10n squared plus 44n on the left, and that is set equal to 30. It's a bummer. What would you suggest we move to clear up one of those sides?
Subtract 30.
Subtract 30. Might as well. That certainly has the fewest parts to deal with. So if I'm looking here on the right, if I were to subtract 30 from the right, 30 minus 30 is going to give me the 0 that I'm looking for. But whatever I do to one side of an equation, I have to do to the other. So I'm just going to throw it over here. And on the right, we know, okay, this is 30 minus 30 is 0. Bring down my equal sign. I like what I see there. But here's another question. This 30 we're subtracting from the left, does it have a like term to actually subtract it from?
No.
Why not? What's different?
It doesn't have a variable with it.
So this is the only term we're bringing over that does not have a variable. So because this first term had an n squared, the second term had an n, there's nothing to combine it with. That's okay. We ran into a situation like this when we were writing things in slope-intercept form back in Unit 2. If you can't combine them, just bring them all down. Now I'm going to take a moment and think, wait a second, I do know that factoring is coming. So if I was writing these down, I wouldn't want to just write them in any old order. I would probably try to keep them in descending order, just to help me in the later steps. So if I was to write out the left-hand side now, I would have 10n to the power of 2 plus 44n. Those were already there. I now have the minus 30 that I brought over. And again, here comes my pickiness. I'm going to have, I'm going to guess that's how far I'll need to go. So good news now is step 1 is done. We've set the equation equal to 0. So step 1 is done, set equal to 0. We're ready to transition into step 2. Step 2 is all things factoring. So again, I have a quadratic trinomial, so my brain's already maybe starting to think asterisk method. But don't forget, you still have to check for a greatest common factor first. Is there something we can take out of all 3 terms nicely?
No.
Well, it's not obvious, but there is one at least.
N?
Well, they don't all have an n. That's why we couldn't combine that 30 earlier.
2,
2, why do you say 2? What was your thought process there?
because they're all even.
They are all even. I think we mentioned it Monday. Even numbers are great because at the very least, they can all be divided by 2. Now I want to make sure that it is in fact the greatest common factor. Could I go any larger than 2?
I say no.
No? Man, that 10 and that 30 really has me thinking divide by 10.
Yeah.
5.
You're saying 5? 5 would go into 10 and 30, but what's causing a snafu?
44.
That
44.
Yeah, 44 is a little bit limiting there. If I were to check that factor pair sheet, I don't have an extra copy on me right now. But odds are, if we think, actually, let me think about the 10 real quick. 10, its list is very short. 1 and 10, 2 and 5. Well, 10 doesn't go into 44. 5 doesn't go into 44. I'm running out of options very quickly. I would say 2 really is my only option. So again, not a terribly exciting greatest common factor, but still an important one nonetheless. So I'm going to divide all 3 terms by the greatest common factor of 2. So I'm going to have 2 set aside before I divide. 10n squared divided by 2?
5.
5. Are we losing an n?
Just 1.
But we didn't take any away. This days.
Oh,
We'd only take 1 away if we were actually dividing an n out as well. So what about 44n divided by 2?
22.
22n. And negative 30 divided by 2? Oh, Marissa says negative 15. So far, so good. We've set aside a greatest common factor. So technically, we have factored. But when I look inside the parentheses here, I'm still thinking, man, it feels like there's still more factoring that can be done. We've set aside the greatest common factor, but I think we can factor a little bit further. And again, ignore me for just a moment while I do this. I'm looking at that trinomial inside the parentheses and I'm thinking, well, it is still quadratic and it is still a trinomial. I could theoretically still use the asterisk method. So why not? Let's see what happens just for fun. So I've got the 2 set aside. That certainly made my A, B, and C significantly smaller. That's nice. So I'm going to list those real quick. The trinomial inside the parentheses, what's my A?
5.
5. What's my B?
22.
22. And my C? Negative 15. I think that was Marissa. And then I write 5. Silly me. So we're still not done factoring. Yes, we set aside a greatest common factor. That's great. But when we're factoring, we're trying to factor as much as we possibly can. So I'm not done yet. So I'm still factoring. Excuse me. So if I'm using the asterisk method here, we'll have A times C on top. So I'm looking at 5 times a negative 15, which I do believe gives me a negative 75. On either side of that, we'll put our A, which is 5. And on the bottom, I'll put B, which is 22. So then I grab my handy dandy factor pair list because it goes all the way up to 100. I find the 75 and I look at the pairs available. I can't remember how long that list is, and I don't know it off the top of my head. I don't think it's terribly long, but I'm looking for factors of 75 that, well, technically negative 75 that will add to equal 22.
So 3 and 25, but it would be negative 3 and 25.
So 3 and 25 are factors of 75, but you said which one was negative?
3.
Okay. So again, even if you're really confident, it is worth a quick mental check or grab your calculator to check. Negative 3 times 25 will certainly be negative 75. Negative 3 plus 25 would give us a positive 22. So one of them had to be negative to get a negative on top. And Tierra chose the correct one to be negative because if the bottom number is positive, the larger number should be positive. So there are little tricks that you can use to kind of speed that process up, but it worked out quite nicely. So that gives me these two very special pairs of numbers. 5 paired with a negative 3. Don't know why this tool is not working now. There we go. And we have 5 paired with 25. Do either of these simplify at all?
5 over 25 is 5.
5 over 25, you can, well, careful, 25 divided by 5 would be 5. All we're doing is simplifying though. But you can take a 5 out of both. If you took 5 and divided by 5, you get a 1, and the 25 divided by 5 would give you a 5. So that would simplify to a 1 and 5. What about the 5 over negative 3? Tierra's shaking her head no. I would agree. That's going to stay 5 with negative 3. And now that's going to allow me to bring back my variable, which was the letter n. Oops. So we still have our greatest common factor, which is 2. But our quadratic trinomial that was inside the parentheses has now been broken down further using the asterisk method to give me the binomials 5n minus 3 and 1n plus 5. Still equal to 0. Don't want to lose any of the pieces. So just to recap real quick, we did step 1. We moved the 30 over to set it equal to 0. We just completed step 2. Now there's actually 2 things we had to do. First, we set aside the greatest common factor, and then we used what was left inside the parenthesis to run it through the asterisk method. I'm now ready for step 3, which is to set each of these factors. This time it looks like we have 3 of them. Set each of them equal to 0 individually. And again, and you don't have to do this on your assignment. I'm just doing it for the notes. But this is where the zero product property comes into play. The zero product property says that since we have a product of a monomial times 2 binomials, and that product is set equal to 0, then at least one of those parts must also be 0 itself. And we consider all possibilities. So either 2 has to equal 0, or 5n minus 3 has to equal 0, or n plus 5 has to equal 0. How would you solve the first?
You just divide 2.
Divide 2 by both sides? Well, sure, then you'd get 1 equals 0. Still feels kind of wrong.
2 times 0?
What's that?
Can you do 2 times 0?
Well, yes, technically, but let me ask you real quick. What are you solving for in this first one?
0.
Solving for 0. Why do I need to solve for 0? 0 is 0.
Solving for 2.
How am I solving for 2? 2 is always 2. I know these numbers. What do I typically solve for? I like them set equal to 0. But if I'm solving for something, it's usually something I don't know. And something that I don't know is often referred to as a variable.
It's too early for brain teasing, my guy.
It's not a brain teaser. We've been doing this for so long. Miranda's saying nothing. You can't solve. There's no variable to solve for. In fact, when you stop and take off the blinders because you're getting tunnel vision, if I told you 2 equals 0, is that true?
No.
No. It's a false statement. It doesn't get me anywhere. I don't have a variable. I can't do anything with it. So although it was an important piece of the process so far, it ceases to be useful because it is not a true statement. There's nothing to solve for. I'm done with it. It served its purpose. So I move on to the second one here. How would I solve this one? So it does have a variable. I can solve this one. That's good news.
Add 3.
Add
To
3 to
0.
both sides. Okay. So that gets rid of the 3 on the left, leave me with 5n. 0 plus 3 on the right gives me 3. Then what?
Divide by 5.
Divide by 5. Miranda's there too with us as well. Shout out for Miranda. 5 divided by 5 on the left is gone, leaving me with just n. On the right, 3 divided by 5, I'm going to get a decimal, but I happen to know that 3/5 is already simplified as a fraction, so I'm happy with that. Then I move on to the last one here. How did I solve this one? Oh, what did I do? There we go.
Subtract 5.
Subtract 5 from both sides. So n is now by itself. 0 take away 5 is -5. First little equation didn't give me any answer. The second one gave me 3/5. The third one gave me -5. So I ended up with a total of 2 solutions, which include 3/5 and -5. No, I will not grade you on how well you can write those braces. That would just be rude of me.
I would fail. I keep trying. It's not. It's getting better, but
It comes with tons and tons of practice. And even then, sometimes I halfway through drawing one, I have a mild stroke or something, and it turns out real wonky. So all right. So again, we've got a little bit more, and I got a little sidetracked today, so it was taking a little bit longer. So we'll probably go over a little bit, but I want to make sure we have time to practice it. Technically, though, everything we've been using so far is just recycling all the skills. Well, not all the skills, but all the skills used here are just recycled from past lessons. Factoring, we've done a few days of that. Solving for equations, we spent units on that, getting variables by themselves. We've done these things. We've just never had them packaged together in such a large process like this. But everything we've done today, we've done before. just not all at once. All right, one more, and then of course we have to throw in some word problems. Otherwise, why are we solving these weird equations if there's no purpose? So taking a look at the next one over here, a little bit more involved, but hopefully you notice right off the bat, the first issue that we have, this might be too long, but I'll come back and correct it as always. What's the first issue we have? It's not set equal to 0. So this one's a little bit more involved because we do have 3 terms on the left. We have 2 terms on the right. But I think that we're capable enough, we could maybe move 2 things at the same time, so long as I'm careful. So technically we could move everything off the left-hand side, but I'm kind of lazy. I would move everything off the right-hand side. But there are 2 terms, so technically there are 2 actions that have to take place here. How would you make that 8a disappear on the right?
Subtract it.
Subtract it. So I would have to subtract the 8a from the right, because then 8a minus 8a would be gone. Do I actually have a like term on the left to subtract it from this time? Tara's nodding, so I would agree. I assume you're looking at this negative 1a that's sitting there. They both have an a, so that must mean that they're like terms. So I'll line those up. But if I wanted to also move the negative 4 here, what would I do differently?
Add 4.
I could add 4 because negative 4 plus 4 is 0, which is ultimately what I want on one of the sides. And I'm going to unlock again because there's also that negative 14 on the left that is a constant like 4 is. So I can line those up because those would be considered like terms as well. So when I go through and clean this up a little bit, I didn't have anything to do with the 7a squared, so it just comes on down. The negative 1a minus the 8a is going to give me a negative 9a, and the negative 14 plus 4 is going to give me a negative 10. Bring down my equal sign. The other side is exactly the exact thing that I wanted to happen has happened. I've taken everything away. It is now set equal to 0. Okay. So step 1 is done. Everything is moved to one side. The equation is now set equal to 0. Step 2 is to factor. What do we always check for first when we factor? Well, we always look for like terms, but that's not necessarily what we're carrying. Greatest common factor is what we're really interested in with factoring. So I see a 7a squared, a negative 9a, a negative 10. I can already take the variables off the table because the last term doesn't have any to give. But what about those coefficients? 7, 9, 10.
You can do 7a and negative 9a.
Those aren't the same. Greatest common factor has to be the same all the way through.
I can't think of anything because they're all different. There's evens and odds.
Some one's even, the others are odds. Miranda's saying just a 1. Well, I would agree because right off the bat, 7 is a prime number, which means its only factors are 1 and 7. Well, 7 is not a factor of 9. It's also not a factor of 10. So 1's it. 1's the only factor. And is it worth taking a 1 out? No, because dividing by 1 changes nothing. So we've considered the greatest common factor. We've decided there isn't one. So I'm ready to try something else. Well, I'm looking at this. I see it's quadratic. I see it's a trinomial. My next thought is maybe the asterisk method. So what is my A? 7. What is my B? A negative 9. And what is my C? A negative 10. So we're still trying to factor. We're still in step 2. So on top, we'll have A times C. So I'm looking at 7 times a negative 10. Oh, should be a negative 70. It's A times C, not A times B. On either side of that will be A, which is 7. B on the bottom is negative 9.
Oh, never mind.
So I'm looking for factors of negative 70 that also add to equal negative 9. So if you have the factor pair list, this makes it a little bit easier because you don't have to find all of them all over again.
I got 5 and 14.
5 and 14.
I think that 5 will be negative. I didn't check it yet though.
She's thinking the 5 is negative. So we grab a calculator, do a quick check. What's negative 5 times 14? Negative 70. Check the second one for me though, please. What's negative 5 plus 14? It's a
That's
positive
right.
number.
Yeah.
Whoops, what do I want?
Negative 9.
I want a negative 9 because of the negative 9 on the bottom. Well, I'm in luck. If you got as close as the right number with the wrong sign, odds are switch the signs. Because 5 times negative 14 is still negative 70. 5 plus negative 14 should give me that negative 9. So we get these two pairs of numbers. Do either of them simplify? Well, the 7 and 5 are prime numbers, so those certainly can't. They don't have anything in common to simplify. But the 7 and 14, I certainly think they have a greatest common factor we could remove.
Turns into 1/2 or 1 negative 1/2.
So 1 over a negative 2, because they both could remove a 7. Now, Miranda, I'm going to nitpick on you real quick, and I'm going to attribute it to the fact that you're typing and not because you actually would have written it this way. But it's very, very important that the negative sign stays with the 2 and doesn't accidentally move up with the 1. So I assume that if you were handwriting this out, you probably would have kept it as such. So, but worth mentioning for anyone else who's still a little bit hesitant. It's already simplified down. We have our pairs. I bring back my variable, which was the letter A. So I now have the two binomials, 7a plus 5 and 1a minus 2. Still set equal to 0. Naturally, I put a little guideline in that was way too long.
I keep forgetting to write that 0 at the end of it.
Yeah, it's very important that we still have it there because without it, we can't apply the zero product property. So we need this product, this case two binomials, we need it set equal to 0 because step 3, where I need to set each factor equal to 0, is all thanks to that zero product property yet again. So either the 7a plus 5 will have to equal 0, or the a minus 2 will have to equal 0. Again, we don't care which one is true. We consider both. How would you begin solving the first? Subtract 5 from both sides. So that removes it from the left, leaving me with 7a. 0 minus 5 is negative 5. Then what? Divide both sides by 7. 7 divided by 7 on the left simplifies to 1. Goodness gracious, my screen freaks out. My a is now left by itself. -5 divided by 7. My calculator is going to try to tell me to do a decimal. I'm just going to make sure it's simplified. And in this case, the fraction is simplified. I get a -5/7. I move on to the second equation. How would I solve that one?
Add 2.
Add 2 to both sides. So the -2 plus 2 is gone on the left, leave me with just the a. 0 plus 2 gives me 2. So when it's all said and done, I end up with 2 solutions, which are -5/7 and +2. So again, it's a bit of a process. I won't sugarcoat it. But that organization and that writing neatly that I harp on you about, and I have been for weeks now, really starts to come into play here, because you need to be able to follow your own steps. You need to be able to trace where your work is going. If you're trying to crowd it into a small space, don't. Grab some extra grid paper or line paper. There's no limit on how many work pages you give me. Take as much space as you need. Excuse me. All right. So all of this was building up to a point to where we can then solve equations that describe real world events. Again, real world means actually happens in the world around us, but doesn't necessarily that means it's going to be events that we run into every single day of our lives. So we have 2 different applications here take a look at. The first one is an example that you may find in something like a physics class, or if you're an astronaut, or really all sorts of situations where we're measuring the height of an object traveling through space at any given time. So here it says that a fireworks rocket is launched from a hill above a lake. The rocket will fall into the lake after exploding at its maximum height. The rocket's height above the surface of the lake is given by a function, and we haven't really done much with function notation, but this is read as g of x equals -16x squared plus 64x plus 80. Now, if you're a little bit hesitant by this g of x, imagine that was just a y, or we'll see what we replace it with here in just a moment. So this tells me that g of x is representing the height of the rocket, and x is measuring the time in seconds. So if you think about it, if something's going through the air, those are probably the 2 first things you'd be interested in measuring. How long is it in the air? So from the point that it is launched to the point that it lands, what's going on in that interval of time. And then g of x is measuring the height at any one of those seconds from the point that it's launched. Now, where we're most interested in is the actual question itself. So there's a lot of information here, a lot of backstory, where the math that we're interested in is the function that it gives us and what each piece of the function represents. But where we start to pick through what we're actually looking for is in the very, very last question itself. How long will it take the rocket to hit the lake? Well, picking through that statement, if I'm asking you how long, am I looking for height or am I looking for time? I'm looking for time. So I'm, oops. So how long we need to find the time, which is our variable x. And then it says, will it take, so how long is what we're looking for, but it also tells us that the rocket hits the lake. So if we're looking for x, then hopefully we know what g of x is, the height is. So let me ask you this. The moment we're considering is when it hit the lake. What is the height of the rocket at the exact moment it hits the lake?
It would be 64x.
This is one of those kinds of questions that's so easy, we overthink it. If you were to stand up right now, if you're standing on the ground and you jumped, you'd go up, your height would increase above the ground, and then it would come back down to the ground. And when you landed back on the ground, what is your height above the ground? 0. Once you land on a surface, in this case it's hitting the lake, but if you were to land on the ground or wherever, its height is 0 because it's no longer above anything. So when the rocket hit the lake, that tells me that the height equals 0. Maybe I should say that g of x, which represents the height, equals 0. So I'm trying to solve for x. The height at which time I'm looking for, I know that the height of the rocket will be 0 when it touches down. So when I take this function I was given, g of x equals negative 16x squared plus 64x plus 80, I'm looking for x, but I know that g of x is 0. Come over here and write this down. So I will have 0 equals negative 16x squared plus 64x plus 80. And again, I was able to replace the g of x with a 0 based off of the context clues of the question itself. The moment it hits the lake, its height is now 0. I need to know when. How long was it in the air, and at what time did it hit the lake? So with that replacement there, I now have, if you think about it, I have a quadratic equation because the highest exponent is a 2. And we're in luck, it's also already set equal to 0. So the first step that we've been working with today is already completed. But I still have some work to do. It is set equal to 0, but I do still need to factor it. And what do I always check for first when I'm factoring?
Like terms.
You did this earlier. Not like terms.
The greatest common factor.
Greatest common factor. At least you're consistent, Toby. Is there a greatest common factor for these 3 terms?
I got 16.
16. 4 would work, but it's not the greatest. And 16, again, probably wouldn't be the first thing you think about, because 16 going into 80, unless you check that list that I still need to give you, Toby, you may not see it right away. But we can take out a 16 from every single one of these terms. So this is my greatest common factor. So I'm actually going to throw you guys through, I'm going to stretch your mental abilities here. I'm going to put the greatest common factor at the other end after I finish my division. So negative 16x squared divided by 16 is going to give me a negative 1x squared. 64x divided by 16 is going to give me 4x. And 80 divided by 16 is going to give me 5. And my greatest common factor is still there. So we're still going through the same process. It just looks like it's a mirrored image of it. Now, I'm not done. I still need to try to factor a little bit further. And I'm looking inside the parentheses, I see a quadratic trinomial. Hopefully at this point we're thinking, asterisk method yet again. So because of the sake of space, I'm going to kind of reorganize how I typically write my information here. What's my A?
-1.
Is a -1. What's my B? 4. And my C is a +5. So then I set up my little asterisk here. I have A times C on top, so I'm looking at -1 times 5, which is a -5. A on either side is a -1, and B on the bottom is a +4. So I need two numbers that multiply to equal -5, but also add to equal a +4. We're in luck. There's only one pair of factors for 5, and it's 1 and 5. The trick here is going to be playing with those signs. Well, since there's only one pair of numbers, it must be 1 and 5. But my question would be, Miranda suggests 1 and a -5. Let's do a quick check. 1 times -5 would give me a -5. That's good. What's 1 plus -5? -4. Uh-oh. I need a +4.
So you make a 1 negative.
So let's switch it. Let's try it this way then. So -1 times 5 is -5. -1 plus 5, +4. That's a little bit more promising. That's what I like to hear. And now I have these two unique pairs to work with. Now this one, because of all the negatives, this one is going to simplify a little bit different. Because if you look at the left-hand side, what happens every time we have a double negative?
Positive.
It becomes positive. That double negative really could just be simplified down to +1/1. Now the -1/5, there's not really much more I can do there. But I can now bring back my variable x and move it on top to get two binomials. So this process, I have to write it over here now. I should now have 0 equals the binomial x plus 1 times the binomial -1x plus 5. And don't forget your greatest common factor, the 16. And just for the sake of consistency, that came from over there to the left. So we have factored it as far as we possibly can. So that finished step 2. Step 3 then says, according to the zero product property, because we now have a product of two binomials and a monomial, and that product is set equal to 0, the zero product property says that at least one of those pieces themselves must be 0 or equal 0. So either x plus 1 equals 0, or -1x plus 5 equals 0, or 16 equals 0. Now, hopefully from the strife that I caused you guys earlier, can we all agree that 16 does not equal 0? And since there's no variable, is there anything I can do with that last one?
No.
No. So although it was important and it made our factoring jobs a little bit easier, it's not going to give me an answer. These other two, however, I can knock out. How would you solve the first?
You would subtract 1.
Subtract 1 from both sides. So 1 minus 1 is gone. We get x equals
0,
-1. How would you solve the second one?
You would subtract 5.
Subtract 5 from both sides. 5 minus 5 is gone. So I'm left with -1x equals -5. Then what?
You would divide -1.
To divide both sides by that -1.
The x drops down.
I'm running out of space, so I'm going to write mine off to the side here. I get x equals +5. Now, correct me if I'm wrong, I did find two answers. I found that x equals -1, and I found that x equals +5. And Miranda, I like where your head's at. You're going with consistency. That's how we've been doing it so far. The set of solutions, -1 and 5. But, it's always a but, isn't there? Didn't x represent something this time? It wasn't just a variable. It represented something specific.
Time.
It represented time, which means something for one of our two solutions.
You can't have a negative time.
You can't have a negative time. If you told someone it took me -2 hours to get home, what does that mean? Are you traveling backwards in time? So off to the side here, let's make a little summary statement. Time cannot be negative. So the final answer is that x must equal 5, and I think we were even given the units. I think it was being measured in seconds.
Didn't show that high, did it?
So that, well, we weren't worried about the height. We knew about a specific scenario. We were worried about when it hit the lake. So I don't know how high it went. There is a way to figure that out. But what this tells me is the question was, how long will it take the rocket to hit the lake? 5 seconds. So from the moment that it launches to the moment that it hits the lake, it is in the air for a total of 5 seconds.
So if that other x was a different, like a positive number, would you like add those?
Or would it be 5?
So in this scenario, again, this requires a little bit of knowledge in physics. The greatest number that other variable could have been in this scenario would have been 0. And 0 would make sense because 0 would be the time that right before it launched. So in this case, we got a negative value, which very immediately told us to throw it away. If we had gotten x equals 0 and x equals 5, well, 0 wouldn't make any sense because of course it was on the ground at 0 seconds. We haven't launched it yet. We would then in that scenario say, it must be the 5 because 5 seconds has passed to the point that it then hit the lake. So takes a little bit of imagination, but in terms of the process of solving it, once you get the equation, it's not too bad. It's then knowing what to do with the solution that takes that little extra bit of thought. Last one here. I apologize that today's lesson's a little bit longer. Just for whatever reason, seems like a busy day today. Last one here is a little bit more challenging because you'll probably notice, well, 1, the prompt is significantly shorter, and 2, unlike the one above it, it didn't give us any type of equation or function or anything. All it did was describe to us a situation. And it reads that the length of a rectangle is 3 more than twice the width. Determine the dimensions of the rectangle such that the total area is 27 square meters. So let's dig out that information. First off, the first statement it gives us is that the length of a rectangle is 3 more than twice the width. We're going to need that. We're also told that the total area is 27 square meters. That is factual knowledge we were given. The question, or well, technically it wasn't a question, it's asking us to find the dimensions. Well, in terms of dimensions, it's already kind of in a way said it, but a rectangle, we usually consider its dimensions as its length and its width. So that's what we're looking for. We want to know the length of this rectangle as well as the width of this rectangle. So we actually have 2 pieces to find. Well, let's dig through this. We're told something about the length in relation to its width, and it all comes down to a total area. What do you know? What do you know about this scenario that would tie area and length and width regarding a rectangle?
Length times width? Wait, no, hold on.
Go with it. Yeah. What about it? What is length times width?
Height? No, that's not right.
Height, if you add height in, now you're talking about a 3-dimensional object and you're finding volume. How do you find the area of a rectangle?
Circumference.
How do you find the area of a rectangle? Area equals length times width. So Tierra, you knew that fact, but you were worried that it wasn't correct. Now, if I wanted to simplify this even further, I could write that formula as A equals L times W. Notice I do a slight cursive L because my L's always look like 1s. I just want to make sure there's no confusion there. So we know that the area of a rectangle equals its length times its width. Awesome. I can't solve this if I have 3 variables. Do I have immediately, right off the bat, do I know one of those pieces of information?
Yes.
What do I know?
The area.
What is the area?
27.
27. So according to the facts, we know that the area is 27. Great. So that leaves us with length times width. Now, here's the bad news. Going back to Unit 3, if you are solving for 2 variables, like we did with our system of equations, you need at least how many equations? Tara, you're mouthing it. I think your first answer was right.
2?
2. You need at least as many unique equations as you have variables. Well, we're out of luck because we don't have enough information to write 2 equations. We only have enough to write 1, but that's okay because of the first statement that I highlighted. That first statement told me that the length is 3 more than twice the width. So if I were to write that statement up here, my length is, which is equal to, how do you get 3 more than something?
Multiply?
That would be 3 times something.
Add.
I would have to add 3 to it. What am I adding 3 to? 3 more than what?
Width?
3 more than the width?
3 more than twice?
What's
2?
twice the width? How do you get twice of something? You multiply it by 2. So twice the width is what the length is 3 more than. So the length is 3 more than twice the width. That statement, algebraically written, would come out to this equation right here. The length is 3 more than twice the width. Now, it's probably bringing back horrific nightmares because this looks an awful lot like a system of equations. In fact, if I bring it over here, now it really looks like a system of equations. I know that the area of the rectangle is 27, and to find the area, you have length times width. I don't know the length or the width, but I do know that the length is 3 more than twice the width. So if I have substitution on the brain, I know that anywhere that I see L, since I know that it is 3 more than twice the width, I can replace it with that statement. Well, it just so happens the equation right above it here had an L, and we were kind of mumbling and grumbling over the fact that we had 2 equations. Now, technically, these 2 equations weren't necessarily 2 equations. One was a formula, which we just plugged in what we knew, and the other one was a relationship. What we're trying to do is come up with a very hybridized equation that we can then solve. So this top equation,
Wait,
yes, I'm
why
waiting.
did you put 27 in for W when it was in area?
It wasn't. I didn't put 27 in for W. What's
Oh,
right
I'm
above
sorry.
the 27?
I saw 27, and I saw 2W. I'm like, what?
Yep.
Yeah, my bad, sorry.
Yep. No, this bottom equation came from the first statement up here. The length is 3 more than twice the width. And now that I know what the length is in terms of width, I'm going to replace the length with all that information, which allows me to write the equation 27 equals 2W plus 3, which is my length, times the width, which I still don't know. We're getting closer. We now have an equation, and how many variables are in this equation?
Oh, what?
1. It is in 2 places, but there is only 1, which means this is solvable. But what's catching your eyes first?
The parentheses.
Those parentheses. What do we usually do when we see parentheses?
Distribute.
Typically we distribute. What are we distributing here?
Nothing.
Uh,
A 1.
What's outside the parentheses?
A 1.
Not just a 1,
A 1W.
a 1W. If I was to distribute this 1W times 2W, I would get 2W squared. And then W times 3 would give me 3W. Now, that was a little frustrating because we had to go through some elementary knowledge. Area of a rectangle equals length times width.
That's elementary.
Oops, that was elementary. We then had to fill in the area with the area that we knew, and then we had to take the relationship we had to come up with this equation. And even then, the equation still didn't look like anything we had done today. So when we distribute the W, is this now a quadratic equation? Tara's shaking her head yes.
Sure.
What does it mean to be quadratic?
It has to be solvable.
Not necessarily, because linear equations are also solvable.
It needs to be solved using quadratic formula.
No, that's actually tomorrow's lesson, ironically. The highest exponent in this equation is a 2 on the variable.
Okay.
If it's a quadratic equation, can we follow the steps we've been doing all day today?
No. Aren't they different?
I think the title of today's lesson was Solving Quadratic Equations Using Factoring. And then it says solving quadratic equations. If this is a quadratic equation, we can in fact use those steps. Here's the problem though. What is this equation not equal to?
0.
Not equal to 0. What would you move?
27.
How would you move the 27?
You can subtract it from 3 3W, right?
Well, I don't think
Or
they're,
you just bring it over.
yep, just bring it on over because there's no like terms to combine it with. Now, at this point, some of you are like, my goodness, it feels like it was so long ago that we actually read this prompt. These numbers are losing meaning. That's okay. The important part was is that we got to this relationship here. What we do from that point on should just be the process we've been using all day. So I'm setting it equal to 0 first. So I get 0 equals 2w squared plus 3w minus the 27 we subtracted over. So that was step 1. Move all terms to one side accordingly to set the equation equal to 0. Step 2, factor. What do we always check for first when we factor? Greatest common factor, not like terms. Greatest common factor. Is there one that we can take out of 2w squared, 3w, and negative 27? Miranda's saying 1. Is that the greatest?
Yeah.
I think so because, well, 2 is a prime number. Its only factors are 1 and 2, and 2 certainly doesn't go into 3. Not nicely anyways. So 1 is the greatest common factor here. That's not going to help me get it any smaller. But then I think, wait a second, why not use the asterisk method? Okay. So let me think here. Where am I going to put this? Goodness. What's my A?
2.
A is 2. What's my B?
3.
What's my C?
20. Negative 27.
Negative 27. So again, this is starting to feel routine again, hopefully. So if I use the asterisk here, I'm going to have A times C on top. So 2 times a negative 27, which I believe is a negative 54. A on either side is a 2. B on the bottom is a 3. I need 2 factors of negative 54 that also add to equal 3.
6 and 9.
6 and 9?
It'd be negative 6 and 9.
Negative 6 and 9. All right, quick check. Negative 6 times positive 9 is negative 54. Negative 6 plus 9 is a positive 3. So we're in business. Do either of these two pairs simplify?
Yeah, 2, 6 turns into 1/3, or 1 over negative 3.
1 over negative 3 here on the left. 2 over 9, however, it's as far as it goes. Bring back your variable, which this time was a w. And through this process, this equation now is 0 equals 1w minus 3 and 2w plus 9. So that was step 2. We factored it completely. It's still set equal to 0. We bring back our new friend from today, the zero product property. Which says that if you have a product of multiple things and that product is set equal to 0, then at least one of the parts of that product must equal 0 itself. So either w minus 3 equals 0 or 2w plus 9 equals 0. Oh no. So 2 little equations here. How would you solve the first?
Add 3.
Add 3 to both sides. Eliminates from the left. we end up with W equals 3. What about the second one?
Subtract 9.
Subtract 9 from both sides. I get 2W equals -9. And then what?
Divide 2.
Divide both sides by 2. And because we're dealing with measurements here, I'll go ahead and do that division. I think we get -4.5. That's what the calculator will tell us. But then I need to ask myself, was W just a variable or did it represent something?
W represented the width.
W represented the width. Which one of these rubs you the wrong way?
Negative 4.5.
-4.5. Why does -4.5 bother you?
Because you can't have a negative width.
You can't have a negative width. You can't have a negative distance, any kind of distance.
You can't go negative 17.3 miles.
So we cannot have negative distances. So although we found it and it worked great for the equation, it does not fit the context of the problem. So our width is 3. What's our length?
Length?
Yeah, we're finding the dimensions.
2W plus 3.
2W plus 3. So I'm going to come all the way back over here. We now know that our width, W, equals, what was it? I already forgot. 3. Oh, no. And we know that the length is 3 more than twice the width. So 2 times the width, which is 3. We get 6 plus 3. So the length must equal 9. So to summarize, our length is 9 meters. Our width is 3 meters. What a process. Whew. Thanks for sticking with me, guys. Sorry if you hate me now.